To those of you in Europe, and good morning to those of you in Australia. Welcome to the opening plenary session of the ESIG 2021 Meteorology and Market Design for Grid Services workshop. I hope you were able to tune into the keynote session we had on Tuesday with Gary Giernart from the Climate and Environmental Sciences program at DOE. And I promise you another quite informative and educational opening plenary session today. I'm Charlie Smith, the Executive Director of ESIG, and I will provide a few brief opening remarks. As I think you know by now, our workshop sessions are all being held online and are open to everyone. And I do want to let you know that we're planning our first major in-person event since the COVID outbreak last year with a fall technical workshop in Austin, Texas during the week of October 25th. Keep your fingers crossed. Please mark your calendars and look for additional information in the near future. This workshop was planned with the input of our ESIG Offerings Committee, chaired by Bethany Frew of NREL and Julia Matoiva-san of ERCOT. The committee consists of the chairs of our 6 working groups and several of our board members. We have a great set of volunteers who really make ESIG what it is, and we encourage you to become involved if you're not already. You can find us on the web at esig.energy, send an email to info@esig.energy to get our monthly newsletter, and follow our activities on LinkedIn, Facebook, and Twitter. ESIG also serves a leadership role in the Global Power System Transformation Consortium, often called GPST, whose mission is to bring together key actors from around the world to catalyze a rapid clean energy transition at unprecedented scope and scale. ESIG leads one of the 5 pillars that deals with the research agenda for the system operators. More information on GPST can be found at www.globalpst.org. Regarding logistics for today, I would ask you to note that the opening plenary will be 2 hours long. We had a lot of feedback that our 1-hour workshop sessions were too rushed, so we have moved to some longer formats for this workshop. We will have a number of individual presentations of 20 minutes each in the first part of the session, followed by 30 minutes or so of discussion and Q&A after the last speaker. As we are doing with all of our webinars now, we will be using the Slido platform for managing the Q&A. You should go to slido.com on your device and enter ESIG4 as the event code to ask your questions. Please be sure to indicate the person to whom you're addressing the question. The instructions are also at the bottom of the background slide for the webinar, and you'll be reminded by the session chair. You'll see a thumbs up button next to the question on Slido to allow you to vote on prioritizing the questions submitted. So please keep the questions coming during the presentations, and we will address them at the end. We will follow up with written answers to any questions we don't get to during the Q&A. Recognizing the limitations of a webinar with more than 100 people on the lines will be muted. So again, we ask you to use the Slido platform to ask your questions with ESIG4 as the event code. Today's session is titled Meteorology and Climatology, the Texas Event Part 1. This session was planned just after the ERCOT blackout in February, and due to the sensitivity surrounding the event, ERCOT personnel are not able to speak publicly on the event at the present time. But we have a great lineup from outside ERCOT who can speak, and I am looking forward to a really great session. This Part 1 session of the February event will cover the meteorology and climatology surrounding the event in Texas and the Midwest, and our closing plenary session at the end of the month will cover Part 2, the energy adequacy and market design considerations in ERCOT. It's important to note that the common mode failures introduced with a correlation between weather, load, and generation will also call for new planning methods in the future. Aaron Bloom of NextEra Analytics, chair of our System Planning Working Group, is making a guest appearance to chair our session today due to an urgent family situation with Rick Walker. Aaron is a familiar face to anyone who has been participating in ESIG and brings a lot of energy and insight to everything that he does. He's a good friend and a good friend of ESIG, and I'm very happy that he is able to be here with us today to fill in for Rick as session chair on short notice. Actually, it was about midnight last night. Aaron, really appreciate your participation, and I'll now turn it over to you.
No problem, Charlie. Glad to be here. I think my favorite sharing sessions are the ones that I get asked to do last minute. Remember when I had to fill in for Eric Ela in Sacramento once, and there was a topic about market design, and I had a really great time. So I'm super excited to be here today because I think this is one, a fascinating topic, and two, the personalities that we brought together with Julie, Justin, Josh, and Congcong are really great, and they're going to give a lot of perspective on it. So as Charlie mentioned, we're going to do 20 minutes per speaker, and we're going to hold questions to the end. Please, please, please put your questions in Slido. They're going to help us have a good conversation and really raise the topics that are important to you. I don't think that there's a utility in the country that hasn't looked at the Texas experiment and said, hey, what would happen if it was our system that was faced with some extreme events? So I think we've got a lot of great opportunity for discussion and questions. We're going to kick it off with Julie Lundquist doing her presentation. She's at the University of Colorado. She's also got an appointment at NREL. She's frequently been here before and offers a lot of great perspective. After we have her talk, we'll go over to Justin Sharp and he'll give us some of his perspectives, followed by Congcong sharing her experiences at the MISO during these extreme weather events. And then we'll close with Josh. So with that, Julie, really glad to have you here. Love that background, and why don't you take it away?
Great. Can you hear me now, Aaron?
Sure can.
Super. Okay. Thanks for that very kind introduction. And Charlie, thank you for the invitation to speak here today. This is a really exciting event, and I'm sure that many of you have been getting questions from your friends and family about it in different contexts. I'm here today to give kind of a large-scale weather and climate perspective about these types of events. And then as we go through the discussion today, then we'll actually be zooming in on this particular event and then how it manifested in power systems. So we have a lot of experience thinking about climate variability and how that affects wind resources and solar resources. When I attend panels like these, I really like to go away with recommendations for papers to read to learn more. So here, I'm giving you on the very first slide an example of one paper that talks about different atmospheric science challenges for wind energy, and some of these climate variability questions are mentioned in that paper. So of course, if we want to think about renewable energy power production, we have to think about global dynamics. And that's going to be the focus of this presentation here today. So we need to think about very large planetary scales. And so I'm going to be introducing a theory about planetary scale variability and explain what evidence there is and what evidence there isn't for that theory and how that may or may not have been related to the Texas event. So I'll give you a little bit of a spoiler here. My conclusion after surveying the literature is that there's really no clear consensus right now about whether anomalously strong and long duration cooling, such as what was experienced in Texas in February, is related to any particular aspect of anthropogenic climate change, especially Arctic amplification. And so I'm going to talk about temperature changes in Texas. I will demonstrate that yes, the Arctic is warming abnormally fast and faster than the rest of the globe. And I'll explain this Arctic amplification idea. I'll explain the mechanism that was proposed several years ago for how Arctic amplification might affect the jet stream and blocking frequency and how that is related to mid-latitude weather events. And then I'll go through a discussion of the current analyses of these types of events. But the conclusion that I've come to, and what I think is reflected in the current scientific literature, is that if there is a relationship, it's a very complex one, and it's very difficult to distinguish anthropogenic climate change from the role of internal climate variability at this point. And so hopefully that large-scale climate picture will lay out the groundwork for Justin's presentation of the meteorology of this particular event. So, all right, let's think about Texas in general. And so it's kind of fun to think about the average temperature scales in Texas. And so I like this image because it's giving us a time series dating back from 1900 to current times of a bunch of different reanalysis products that you see here highlighted in the lighter colors. And then the observed Texas heating, or the observed Texas temperatures in bright red. As you can see that the general trend overall is that temperatures in Texas are increasing rather than decreasing. If we zoom in on specific regions in Texas, And if you guys look at my slides later, I have all of the documentation of where these data came from in those slides, so you can look at them. But everybody is positive in terms of increasing temperatures over the course of the state of Texas. Now, of course, we're thinking about a particular extreme event, so these averages and annual temperatures might not be reflective of that, but I think it's important to remember that the larger context is that we have warming. So now as we shift up in scale, or up in latitude actually, let's move to Arctic regions. So these are kind of complicated plots to look at, so I'm going to walk you through them very carefully. So in panel A, we have a time series from 1960 to present as a function of latitude. So we've got the equator here in the middle. We have the Arctic up here north of 60 degrees north. And these colors show the temperature anomaly compared to some baseline. And what the authors of this paper have highlighted here is that there is a lot of very strong warming in the Arctic that is stronger and faster than the warming that we see in other parts of the globe. And so if you compare that warming, if you take this average over this latitude band, then you end up with the blue line in this time series here. The red line represents an average of land temperatures between 30 degrees and 60 degrees north. And then the green line is just the difference between those two. And so we have one temperature trend in the mid-latitudes, Texas and environment and that band. And then you have a different trend that's in the Arctic. So this is the idea of Arctic amplification, which I tend to abbreviate as AA throughout this presentation. So again, we see that that is definitely stronger in the Arctic Ocean in autumn and in winter. And then in the summer, there are some other shifts that are relevant as well. But the idea of Arctic amplification is a super fast, super strong warming in Arctic regions. All right, so I'm sure that you have seen many fun or distressing, not really fun, I mean, the visualization is fun, but distressing images of time series of sea ice extent and how rapidly it is eroding. This is one that I pulled off of Twitter actually a couple of days ago from Zachary Labe, showing how in one part of the Arctic, this is the Laptev Sea, if you think about the sea ice extent in 2021, this year, it is already lower than it has been in any previous years. So the sea ice extent and how it's changing is both a cause and an effect of Arctic amplification. There are lots of complicated nonlinear feedbacks going on up there. Okay, we can also see Arctic amplification if we look at reanalysis data. So people who do this kind of scale of climate analysis consider reanalysis products, which some of you may use for your wind resource assessment or solar resource assessment. You might use MERA or ERA5, those types of products, as kind of a model, but people who do climate work think of them as observations because there are so many observations integrated into the modeling system. So here we have 4 different representations of what is happening in the Arctic latitudes. So here on the x-axis, we have something from 45 degrees north up, or actually this is probably from 30 to the North Pole. The angry red colors show the temperature trends over the course of a decade. And I think that this was 30, yeah, this is 30 years. And you can see that in the reanalysis data, the best guess that we have of observations, you can see very strong warming in the Arctic close to the surface, and you can also see it very high up in the upper atmosphere. That is not reflected in some of the climate model forecasting runs. Here's an example of CMIP5 using a very aggressive carbon dioxide increasing scenario where you only get the warming at the surface. There's another model intercomparison study that model mean gives us warming at the surface. But if you take the individual best member of that ensemble, then you get warming at the surface extending all the way up into the upper atmosphere. So this idea of Arctic amplification is well accepted, and there is consensus that it is happening. Now, the question becomes, how does that affect mid-latitude storms and mid-latitude processes and just the general weather in the mid-latitudes? So that brings us to looking at observations where we compare the temperature anomalies that we see in certain seasons. So this is January through March for certain durations. And so this type of study is very sensitive to what is your beginning year and what is your ending year in your analysis. The theory is that we've got this warming in the Arctic and it is somehow influencing mid-latitude weather. And next I'm going to talk about the processes through which that Arctic warming can be influencing what's happening in the mid-latitudes. So I really like this flow chart, which came from a review article. So we care about mid-latitude weather. We care about anomalously cold events and long duration events like what we saw in Texas in February. So we care about this in the red box. The problem is that this, in the white box, the red text in this box is influenced by lots of different phenomena. So we have changes in storm tracks, changes in the jet stream and planetary waves, which we'll talk about next. That is in turn influenced by natural variability in the climate system, as well as what's happening with the polar vortex, what's happening with sea ice and the cryosphere. How is that changing? How is Arctic amplification directly influencing the jet stream and planetary waves? How is that influencing the cryosphere? And then that feeds back and so on. So there's a lot of different processes going on that are difficult to disentangle. All right, so if you were fortunate enough to take meteorology classes, or if you just have a strong interest in meteorology, then of course it may be fun to think about the jet stream. So as you remember, hopefully remember, or maybe have never heard about before, the jet stream is this very strong westerly flow that is generally located in the mid-latitudes, and it is a function of Rossby waves. So if we think about Rossby waves, this is a result of the fact that we're on a rotating planet. So these are waves that we see in the jet stream. These manifest as trains of alternating weather patterns. So we can look at this positive vorticity region here, this negative vorticity region here, and we can see that we have cyclones and we have anticyclones. So anticyclones in the northern hemisphere are high pressure systems where we have very stable weather with sunny skies and very quiescent winds. When we have cyclones, this is very dramatic weather. And so the magnitude of these oscillations is pretty important. And the rate at which these Rossby waves propagate towards the east or from the west is very sensitive to what's happening in the overall atmosphere. So if we didn't have, there's a very delicate balance between the ambient background flow, the ambient background westerlies that we have, and the manifestation of these Rossby waves. So in some cases, there can be a balance between them so that these waves, instead of propagating from west to east, they may actually end up being stationary, which can be very problematic because if we have stationary waves, then we have long duration weather systems in specific locations. And if we have a large scale persistent weather pattern, that's known as a blocking event, and that can either be an extended region of really nice weather or an extended region of very detrimental weather. So thinking about that balance is really important. Okay, so here's another visualization. We can think about the jet stream as being kind of a manifestation of the polar vortex structure. So if we're thinking about going from mid-latitudes up to northern latitudes, it's not always correct to say that the jet stream follows this white line, but for the purposes of this presentation here, we'll go ahead and acknowledge that we can have waves that are very smooth, like what we see here on the left, and then we can also see a lot of oscillations in this example here on the right. So before I mentioned high pressure systems and ridges, so what we see here in the Eastern Pacific, we have an example of a ridge here. So this would lead to anomalously warm temperatures in this location. And over here, we have anomalously cold weather in this location because we're bringing Arctic weather down south. So the thing I want you to remember here is that there is a lot of variability overall, variability from week to week, and then variability from year to year. All right, so there has been a theory that was proposed called how Arctic amplification would affect weather in mid-latitudes. So the idea is that the strength of the winds here is partially driven by the temperature contrast between the Arctic and the equatorial regions. So if you reduce that temperature contrast by making the Arctic warmer, then you're basically causing slower winds in the zonal direction, or winds that are moving from west to east. So if you have those slower winds, then those winds that keep those Rossby waves rotating around the planet, those are not going to be as efficient at making those systems rotate through. Okay, that's the first effect. The second effect is that if you have enhanced high latitude warming, then you can take these ridges that used to be in the solid line and turn them into this dotted line so that we have more extremes where the blocking is stronger, where the ridges are higher and the troughs may be deeper. So we would have both of these effects causing slow progression of Rossby waves towards the east, which means longer lived events. And then this leads to increased likelihood of drought, prolonged precipitation, and so on. So this was the theory that was presented in 2012. And there's been a lot of discussion in the literature since then. And I think a lot of it made it into the popular press in the context of the ERCOT event. So I'll give you a few more pieces of evidence from this. This is actually from the original paper, where they looked at data from 1980 to 2010 and looked at both the geopotential height thickness, which we can just think of that as a proxy for the temperature difference between the equator and the pole approximately. And then we can also look at the zonal winds. And so the authors looked at, in particular, the fall, October, November, December, and the winter, January, February, March. I noticed that, okay, that zonal thickness or that geopotential height thickness is decreasing. And at the same time, look at this, we've got decreasing winds. And so this is causing a slowing of the polar jet stream, which they argued would lead to more long-lived and persistent events. Okay, here's another example where they are plotting the jet mean speed. And so this is in blue, but it's actually the negative of this. So when we become negative, then it's actually stronger winds. And then we have the latitude standard deviation and the number of blocking days. So the idea here is that we have weaker jet streams, and that leads to increased blocking events or slowly progressing Rossby waves, and then a larger variance in latitude. And that variance in latitude is what we see here, where these dotted lines have a higher amplitude and deeper troughs. Okay, so they see that when they look at a reanalysis product that goes back to 1900, the 20th century reanalysis, then you have more blocks and larger variance in latitude. So they were just looking at the relationship between these phenomena, not necessarily what was the cause. So they did do a careful study of recent decades. I think it was 1970 to present, which was 2000 in their analysis. And they concluded that this was internal variability and not necessarily anthropogenic climate change that was causing increased blocking events. So this is a piece of evidence saying maybe it's not Arctic amplification going on. So this is Libby Barnes' extremely important study that looked at different metrics for how we assess a blocking frequency and changes in winds and changes in wave numbers. So this is a really important piece of evidence in contrast to the argument that Arctic amplification is increasing mid-latitude extremes, because she was able to look carefully at 3 different reanalysis products and recognize that, okay, we have a decrease of wind speeds in most seasons. So we have winter in red, we have fall in blue. Those are probably the most important ones. Summer is in red, winter is in black, and that's particularly important for this event. The crazy thing is that although we have these decreases in zonal winds, the changes in the wave numbers, the actual waviness of the jet stream has shown a pattern that is inconsistent with the theory that was proposed up here. So for example, we have red on the negative side up here, and red is on the positive side down here when we're looking at waviness. And so this was, I think, it may have been the first study, it's the one that I cited most often, looking at how the increase between the wave speed and the winds up at 500 millibars is very complex, and there's not necessarily a clear linear relationship between them. And in fact, there was no evidence that was statistically significant that Arctic amplification would contribute to increased blocking or extreme weather in the mid-latitudes. So we go on from there. This is a very recent overview of the overall literature on this idea of the connection between Arctic amplification and severe mid-latitude weather. And what we see here in this bar chart is a summary of research studies. So observations generally mean analysis of reanalysis products. not of specific observations. So my bias as someone who grew up in atmospheric science doing a lot of observations before I moved into modeling, I tend to think that observations are probably more reliable, but it's really important to recognize here that these observations are first reanalysis products, and second, very sensitive to the choices that you make about which ranges of latitude to study and which years to study. What's interesting is that the modeling studies are very evenly divided about whether or not there is a link between Arctic amplification and severe mid-latitude weather. So I'm urging us to be very careful with our interpretation of the observational studies, and notice that there is a very clear lack of consensus from the modeling studies. And of course, some papers are both in observations and in modeling. So the conclusion here is that simple causality statements cannot yet be made, and the topic is still very contentious. So I would not feel comfortable telling anyone that yes, there's a clear connection between Arctic amplification and severe mid-latitude weather, because I don't think that there is that yet. Now I want to wrap up with this particular figure because I found this very compelling. So the authors of this study basically looked back at that initial 2012 study that said in their conclusions that in the next few years we'll be able to have more data to test this hypothesis. So now we have more data. So what's highlighted in gray here on this time series, and we have many different parameters that we're looking at here, what's highlighted in gray is the data that was used for that original study. And what I want you to notice is the slope of the lines that are fit to just that gray area, and then the slope of the lines that is fit to data before that gray area and data after that gray area. And I'm going to try to zoom in a little bit here for you on what I think is most interesting. So the top bar is the sea ice extent, and of course that is decreasing rapidly as you've seen in what I mentioned before. Arctic amplification is increasing, although it's not increasing quite as fast as it did during that time period. The Arctic Oscillation Index is not important for us now. What's particularly interesting is the waviness in the Rossby waves. So it seemed like that was increasing during that focused time period that was presented in that initial Arctic amplification study. But when we add more long-term data, the sign of the slope has changed and become negative. That is a very compelling thing to me to point out that Arctic amplification is not the entire story for what's happening in mid-latitudes. And of course, we can look at surface air temperatures in different parts of the world, and we can see different trends in the shorter time period and the longer time period. But it's really this change in waviness and the likelihood of blocking events that I think is particularly sensitive. So I should wrap up there and just repeat the conclusions that I gave to you before, and just emphasize again that if there is a relationship between Arctic amplification and extreme weather events in mid-latitudes like the Texas event, it's a very complex one that is mediated by internal climate variability, and there's not a clear consensus as of yet. So I'm really looking forward to the discussion and your questions, and I'm looking forward to learning a lot from the other speakers. So thanks a lot.
Julie, that was awesome. You really set the stage for us there. And Justin, why don't you go and get yourself ready? We're going to hold the questions. Please go to Slido and enter your questions in eSig or for eSig 4 and add your questions to Slido so that we can bring them up here. And Justin will have you turn on your camera and get your content shared.
All right, here we go. Able to see that, Aaron?
Yes, sir.
Right. Okay. Good afternoon, everybody. Good evening for those of you in Europe. I don't know if there's anybody in Australia. Good morning. If I don't even know whether my time zones are right. Thanks to Charlie for inviting me to present today, and I'll get on with it because I want to spend as much time as possible on the panel. So Charlie asked me to basically do an overview of the Texas cold wave that occurred this last February. And I think some of that came out of the fact that when the event happened, I started looking, I saw a lot of these news articles about that were speculating about it being climate change driven, and I was very skeptical about that. So I'm going to sort of take you through the event and then take you through some of the things that I've learned from the data today, and then we'll leave the rest of it for discussion afterwards. So the title is Texas Cold Wave Unprecedented or Not. So I wanted to steal a little from Julie's presentation. She showed this example of sea ice. It's something I often put at the beginning of presentations, is what the current sea ice status is. That's because it keeps me awake at night. This is, in my opinion, along with what's happening in the oceans, really the manifestation of climate change, which is really, really frightening. I'm not an alarmist, I'm extremely alarmed. And I wanted to put the context there because I'm going to say some things a little later on that might give you the impression that I'm not worried about climate change, and I am. So the February cold event was essentially driven by 5 mid-latitude storms. It's often discussed synonymously as Winter Storm Uri. The Weather Channel has started this business of naming winter storms. I confess I don't like it. Winter mid-latitude storms don't look like hurricanes or tropical storms. They don't tend to be coherent and hold themselves together through terrain and things. And so I don't really think they're the same entity when they make landfall and make it through the Rockies. But that's what the Weather Channel's doing. And I know people can get their arms around storm names, so I've tried to use them where I can here. Anyway, Uri was considered as a major coast-to-coast storm that spread snowfall, damaging ice from the northwest into the south, the Midwest, and the Northeast on February the 12th through the 16th, 2021. The storm was followed by the coldest temperatures in decades in the south central states. That's according to the Weather Channel. These pictures here I gathered from the web. The big picture is actually from my front yard after the storm after Uri was making landfall, which is Viola. But Uri was what brought the snow. Viola was what brought the ice. We had over 1.5 inches of ice at my house. That's the most ice I've ever seen. And then the other pictures, one is from Houston, which shows the state of the freeways on February 15th. And the other one is from New York State, just showing you how it went through the entire country. So the national impact, as I said, heavy snow and ice in the northwest where I live. There was 11 inches of snow in Seattle, 5 to 11 in Portland, depending whether you got snow or ice. As I said, the most I've ever seen. If it had not been for Texas, we would have been talking about what happened in Oregon right now. We had over 730,000 people without power in Oregon. There were 200,000 people in Portland alone, just to give you an idea of how many that is. The city of Portland is less than 1 million people. So it was a tremendous event from a distribution standpoint, from the damage to the ice. There's pictures of the ice on the picket fence that you can see around my neighborhood. Tremendous amount of icing. Blizzard conditions into Albuquerque, heavy snow across the plains, snow, sleet, and ice to the Texas Gulf Coast, with 80% of Texas snow covered. I mean, when you think about the latitudes involved there, we've got snow pushing all the way down to 20 degrees latitude. And that picture in the middle is a great pic of sea smoke over the Gulf of Mexico. So the frigid cold air is going out over the Gulf and is causing the water that's evaporating off the ocean to immediately turn to fog and create sea smoke, which is pretty cool. So by February the 16th, 73% of the area of the lower 48 was covered in snow, which is the most snow we've seen for at least 17 years. And the temperatures plummeted behind Uri, but there's more to it than that, and I'm going to walk through that in a minute. And the common mode failures that combined to basically create a situation where extreme demand combined with a lack of resources took ERCOT to within minutes of grid collapse. I've heard some people say they were within seconds. And the power was cut to 4.5 million homes in rolling brownouts in order to maintain the grid. So why did we have such active weather in January and February? Well, most meteorologists will point to a sudden stratospheric warming event that occurred on January 5th. I started watching the weather really carefully after I heard about this. I knew something big would likely happen. We just didn't know when. SSWs occur about every 2 years or so on average, typically in the winter or the early spring. And what happens, without getting into the details, is that the polar vortex becomes weakened. It weakened in late December, with the mean winds reversing in January. And those events basically disrupt the polar jet stream and favor the amplification that Julie was talking about, often for several weeks, up to 6 weeks after the SSW occurs. And that really opens the door for cold air outbreaks and also for warm air moving north. And where that air ultimately ends up depends on the global weather patterns. And in this particular case, we had a Greenland block, which was moderately strong. So Julie showed those pictures of ridges and troughs. So you had a ridge over to the east of the East Coast over Greenland, and you also had a block developing over the West Coast in the beginning of February. And those features basically forced the the cold air down through Canada into the US. And you can see that here in this picture. And I'm not sure if you can see my mouse cursor or not, but we basically have a trough here. So we have my arrows show the West Coast ridge on the left-hand side, and the Greenland block, which is also another ridge on the east side. And in between there, you have this deep trough, which is actually recirculating the air around and has actually become a cut-off low. And there's no progression in the weather occurring at all because it's completely blocked. So what that looks like is, I'm going to show you a quick movie here. As you watch the movie, look at this ridge over on the left side and the other ridge over on the right side, and then the area of blue in between. That's where we have lower than normal heights. You can think of that as lower pressure on a height surface or lower heights on a pressure surface, and basically how the pattern is blocked. And I'll start the movie, and hopefully it shows up on WebEx. And you can see that essentially the flow is unable to exit the region and just spins and pushes cold air all the way down into Texas. If that ridge had been completely blocking downstream over the East Coast, we could have had an even more intense event. But it lasts for over 10 days. So I'm going to walk you through the weather pattern. I'm not going to belabor this. I'm going to go fairly quickly. A lot of the reason I put this stuff in was to fully understand the event myself. The first storm was called Roland. What we've got here is on the left-hand side, upper left, is the time and day. And then there's a trace of the temperature at Dallas. And the red line is the freezing line. So anything below that line is temperatures below freezing at Dallas-Fort Worth. And then I'm going to show you a series of maps. For those of you not so familiar with meteorology, where we have red circles and blue triangles, that's called a stationary front, which basically means it's a boundary between an air mass which is not moving. You have cold air on one side, which is the cold air that's pooled up here. And then you have warm air on the other side. Where it's blue, it means that cold air is moving south. Where it's red, it means warm air is replacing cold air. And there's temperatures that are plotted here. So you can see up in the Midwest, the temperatures are in the minus Fahrenheit range. And over in Texas here, up at Dallas, it's 49 degrees. It's 64 degrees further south, 69 in Houston. And Storm Roland is just moving through Texas. 12 hours later, Roland is through. It really doesn't have a coherent form. It's basically fallen apart, but it has produced a fair amount of rain, of snow and freezing rain up through the Ohio Valley. Heavy snow in the Ohio Valley. And you can see that cold air is migrating to the south. The Midwest surface high starts to build here, the 1034 that you're seeing, that's high pressure building in. And there's air diverging out of that high pressure. So basically air is sinking and then is moving out into the plains. It's very cold air. and it's replacing that warmer air and pushing south into Texas. Also note that there's decent wind resource in this area as the air comes through, and that's important to what Josh is going to talk about. So basically for the next few pictures, the fronts are largely stalled out because we don't have a lot of synoptic support, because we don't have any waves that are moving, they're all just blocked. But the cold air is gradually moving further and further south, and so you can see this front moving south. So I'm just going to play it through and note again that there's a decent wind moving that cold air. You don't move cold air unless you have wind, and that's an important point to note for Josh's presentation. These areas with the dashed lines, those are that's the present weather symbol for light fog. So a lot of these areas around the fronts are seeing light fog, also negative for solar generation, so keep that in mind. You can see the winds strengthen as these isobars get closer together. We've got a stronger gradient, and so we're pushing more cold air to the south. You can see now that the temperatures drop below freezing. Storm Shirley has just exited the mid-Atlantic coast, and the cold air is continuing to sag further south. That air, the cold front is now south of the US border in Texas, and you can see that temperatures are down into the 30s through almost the entire of Texas, with the exception of the coast. And so I'm just going to step through this quickly now. Again, note that correlation between the decreasing temperature and the winds. And now we have what the Weather Channel is called Tabitha, forming in the Gulf. A lot of the reason why these storms are forming here is there's this incredible gradient between this really cold air over the continent and the warm air that's over the warm Gulf of Mexico waters. Again, you can see the wind has strengthened, the cold air is coming through, and that's dropped the temperature again by about another 5 degrees into the 20s. We get a day of warming where there's a relatively sunny day and briefly overwhelms that cold air that's coming in. But then behind that, we start to have stronger winds as this gradient tightens. This is Uri now coming into the picture. It's affected the Northwest, it's dropped down into the Four Corners region, and it's about to come through Texas. And now this gradient's really tightened up here and is starting to pull cold air from the north down into Texas. And you can see that now the temperature really starts to crash. We're down below freezing all the way to the Gulf Coast. 12 hours later, we're in the 20s on the Gulf Coast. Dallas is in the single digits. And we keep going, and that front's all the way down into Mexico, which is really phenomenal. This is a once in multi-decades type of event at this point. And we're off the page. The front is all the way down at the bottom of our screen. And we see that behind Uri, the weather is cleared, but even though the weather is cleared, we've still got this incredibly cold air, and the temperatures are crashing at night because we've got clear skies under snow cover, and snow just is a double whammy. It reflects all the sun during the day, and it radiates out like crazy at night. So record lows are being set. And then the pattern slowly starts to translate to the east. And so you can see this high pressure system now, where it says 1027, has become much more diffuse and is moving east. There is a gradient in this region right here, but it's now a southerly gradient. So warm air, relatively warm air, is able to move north. But that air is so cold anyway over Texas that it's not making a huge difference yet. And then the slow moderation continues. And one thing to notice is how the wind resource here has gone almost completely. This high pressure system is weakening, is covering a large area of the country. There's very little gradient, and there's very little wind generation capacity anywhere at this key time when we have really high loads. And that's not to say that wind isn't capable of providing us power where we need it, but this is one of those events that Josh is going to talk about where we've got a weakening of a high pressure system behind a storm. The wind tends to provide us with some power during the storm coming through, but behind the storm we end up with this weakening. Even though loads are starting to drop now, so is the generation capability. And then basically we continue with this moderation, and I'll just step through this quickly in the interest of time. And you can see we gradually moderate, and then we come out and we briefly go back below freezing again. And now the pattern's starting to translate off, and we're actually getting storm systems coming through again. And if we were to look at that upper level flow, we would find that the trough is translated off to the east, and the storm path is now open again. So how bad was it, and how unusual was it? Let's have a look at Dallas. Dallas saw 94 hours below freezing, followed by 2 hours above, and then 160 hours below freezing, which is pretty unprecedented in recent times, and is the reason why it got so much attention. It's impressive for its duration, for its southerly extent, and for its severity. There were a lot of records broken. This -2 here is the coldest temperature we've seen since the 1940s. 1899 was colder, it was -8. But it's not unprecedented. It was cold for longer in 1983. There were 296 straight hours below freezing, and this plot here shows you what happened in 1983, starting the events at the same time. And so 24 hours is obviously a day. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 and a half days below freezing, which is incredible for an area so far south. And also we had, during that 1983 event, we had 42 hours total that were below 10 degrees Fahrenheit, and 97 hours that were below 15, which is double what we saw in 2021. But 2021 did see many more hours that were below 5 degrees, and that's that severity as Uri translated through and dragged that cold air down from the north. It was very short-lived though, fortunately. So how about a comparison of long-lived cold events at 3 Texas stations? I looked at days meeting the following conditions. So for Dallas, I looked for where the temperature was, the maximum temperature for the day was below 32, or below or equal to 32, and the minimum was below or equal to 25 for at least 3 days consecutively. So it never got warmer than those conditions from 1948 to present. And I looked at Houston, which is a little further south and more coastal. So I modified the conditions to less than or equal to 35 Fahrenheit, and also less than 30 Fahrenheit for the minimum for 2 consecutive days, and then looked at McAllen, Texas, which is right on the Mexico border inland, for less than 40 for a max and less than 32. And I did some stats. I'll point, you can sort of look at these at your leisure if you want to grab the presentation later, but I'll bring out some key points. Here's your December 19th to 29th event with 17 days that were consecutive nights that were below freezing, 13 consecutive days where the high temperature never got, sorry, there was the high temperature, minimum high temperature was 13 degrees. There were the minimum low temperature was 5 degrees, and there was 4 days where it never got above 20 degrees at all during the day. So that was one really major event. Another major event that occurred was this December 21st to 23rd event. It was a pretty short event, but the temperature hit -1, so almost as cold as this last event. And then 15 nights of freezing. January of 78 also was nowhere near as cold, but we had 16 straight nights of freezing. And also another one that was really interesting was 73, which was just a particularly cold period for a long time. And then in Houston, what's really interesting is that this last event that just occurred in February didn't even make it onto the list. It didn't even meet the qualifications because the flow generally just was onshore, and so the ocean was warming things up. And Macallan, the event did make it onto the list. Oh, and by the way, Houston during the December '83 event was significantly colder, with a low of 13. And then Macallan, we see again, '83 really stands out, and some of the other events, the December 1989 event really stands out too. One thing to note here is that the 2011 event that was talked about a lot and that FERC did that major report on, that only makes it into the Dallas-Fort Worth table. It wasn't a particularly severe event. Another thing to notice is that these events seem to occur on a cycle of about 22 to 32 years. You can see that there was 32 years between there being high in the teens from the 50s to the 80s, and then 32 years again. Ironically, I'm not saying that they always occur on 32-year cycles, but it is a roughly once every 3 decades type of thing. I think I'm a little over time, so I should wrap up here. So what about climate change? Are these events becoming more common? Well, I wanted to kind of piggyback on some of the stuff that Julie had talked about. So what I did was I grabbed some data from a bunch of different sites, and I've looked at a bunch more of these, but I just did some representative samples. I got 4 stations in Texas, and a station in Oklahoma. Basically, roughly, they're going from north to south, so Oklahoma's the furthest north one. And what I've done here is I've binned the data according to temperature bins. So for less than 2.5 Fahrenheit, 2.5 to 7.5 Fahrenheit, etc. by the legends. And the legends are different because obviously they're in different places. But what you can see here is that there's a general trend towards less days with cooler temperatures. But if we look at the trend for the extremely, so that would be like the overall stack. But if we look at the number of days for the extreme events, there doesn't seem to be a strong signal. We had a lot in the 70s and 80s, and then it dropped down to a minimum in the 90s and the 2000s. And you can see that at most of the stations, and it's picked up again in the 2010s. So sorry about the labeling here. I made a mistake in my script, and they're actually for 2011 through 2021. So they do include this last event, which, you know, it was so extreme that it does affect the statistics. But it's hard to tease out a signal. It does appear that there may be a climate signal that's reducing the number of cold events, but it doesn't seem that the number of extreme cold events can be shown to be decreasing yet. So my conclusions are that February 2021 was a tail event for Texas, but it was not unprecedented, nor was it the most extreme event ever seen in the state. It was arguably one of the top events, though. Many records were set. It wasn't an act of God. We do see it in the climate record. It can be planned for. You know, we have to make a decision as to whether we want to plan for an event that occurs every 35 years or so. But, you know, I won't get into that, into the politics of that. But it was an event that we should have known could have happened. And they have a return frequency of about 20 to 35 years. There's no apparent climate change signal, and overall, the frequency of the extreme cold seems to be diminishing, but the frequency of the most extreme events may not be. But by their nature and samples, the sample size is too small to be definitive. So looking forward to the discussion, and thanks for your attention.
That was awesome. Thanks so much, Justin. It's been quite a lesson so far in kind of understanding what was happening from a meteorological perspective as these events unfolded. So now we're going to shift, and we're going to have Congcong Wang from MISO give a presentation on the perspectives from their system. And so Congcong, if you want to go ahead and start up your screen and start sharing and turn on your video, that would be great. As a reminder, we're holding the questions till the very end. I'm seeing them already coming in on Slido. If you have some questions that you're aching to ask, please go ahead and bring them up, and we'll make sure that we hear them. Congcong, I can see your slides, but I can also see your background that you have open. So just letting you know that.
Just give me a minute to put in the presentation mode.
Great.
Just while it's putting up, can you hear me well? Just a microphone check.
Yes, your mic sounds great.
Okay. All right. Is it up?
Yes, it is.
All right. Hello, everyone. Thanks for having me here today. Actually, today was quite an extreme day for me. We actually spent most of the day in the morning prepare for the extreme hot weather, anticipating in our north region with upper 90 degrees in Minneapolis. And now in the afternoon, start to talk about extreme cold event in the past February. So we'll walk through what we saw in the MISO region during the February cold weather event, especially in our south region. This weather event is definitely one of the most extreme events we've ever seen over the last 30 years or so. As we know, the extreme weather affect a lot of the industries, particularly for grid operations. The extreme weather directly translated into very high demand, tight supply, and also large stress on our transmission systems. So we actually start to pay close attention to this Arctic weather pattern since early February, if not earlier. We work together with our members to prepare in advance, and the coordinated efforts continued throughout the event, especially during the emergency operations. The event definitely emphasized the urgency of the work we outlined in our responses to MISO reliability imperative, which is a living document we developed to work with our members to manage current and future challenges. So as Justin well addressed, what make it a kind of a 1 in 30 event is not only because the extreme cold, but also because the long duration. We see like 20 or 30 degrees below normal temperature during this long cold stretch throughout our region, especially in the south. So just highlight in our Little Rock and also Houston, we saw the coldest 3-day stretch since 1989. And in Little Rock, particularly, the average temperature was barely about 10 degrees. So that's really extreme cold event. Accompanying those extreme cold is heavy snow and ice. We saw particularly in our south region again. And in Little Rock, actually, it set its maximum 3-day snowfall record of almost 20 inches. So for a lot of you know, snow and ice also pose risks on our transmission and generating facilities. So at this point, we don't have much solar in our south region, but in the future, as we anticipate more solar, definitely the snow will cause tremendous difficulty there too. So the extreme weather directly drove high demand, like our south load. Like going forward, we'll more focus on the south because that's the most impactful region, and we would also touch the rest of the system where it applies. So for the south load, because of extreme weather, it was driven high all the way close to our all-time peak. As you know, usually summer, the all-time peak is was set in the summer, but this extreme cold definitely set the winter close to the summer peak. On top of the extreme high demand, the extreme weather and load conditions definitely make a forecasting a very challenging task. which is also a very critical task that a lot of our operating decisions are relying upon. So because of the extremeness of this event, we don't have much data available in our load forecasting models. If we plot out the south load and the winter month temperatures, you can see here, you will see very thin distribution when it gets really cold, and not only thin, but also very spreaded or scattered. So like that will cause really difficulty in the forecasting model. Also because of demand activities, like such as the office closure because of the cold or snow, those will introduce more uncertainties for forecasting. And also like the forecast error, we actually saw the weather forecast like throughout the week, we saw like a lot of time over up to over 5 degrees of forecast error in our south. So actually every degree of temperature forecast error can directly translate into several hundred megawatt or even 1,000 megawatt load difference depending on the time of the year. So very impactful on the load side. And as we move deep into the code, we actually saw a large amount of generation outages too, put pressure on the supply side. Again, look at the south, particularly on February 16th or 17th, we saw like 17, 18 gigawatt of outages. That accounts for over 40% of the installed capacity in our south region. So not the best time if you think about the high load, and now simultaneously the supply tight condition. And a lot of those outages attributed to weather or the fuel, given the tight gas situation. And also highlight is a lot of outages are unplanned, which cause more risk management challenges without knowing in advance. So while supply and the demand condition is really stressful, really want to highlight here is another critical component, transmission. Transmission is really vital to move generation to load. But during this extreme weather event, our transmission system was really stressed by the transmission outages and the extreme flow. So here, I would like to ask you all to picture the map of North America. So imagine MISO in the middle, covering 15 states and a Canadian province in our footprint, stretching from Canada to south to the Gulf of Mexico. So let's look at the transmission flow here. Very unprecedented transmission flow pattern we experienced during this extreme cold event. So during this event, we actually got very good help from our neighbor, PJM. We see the scheduled interchange flowing from PJM to MISO and to SPP. These are really helpful for both MISO and SPP, but meanwhile resulted in a very extreme flow from east to west. All right, and then the other direction from north to south. Again, here, the large geographic footprint of MISO really helped during this event. We were able to transfer some of our generation from the north central to help with the south situation. But we have a contractual limit between MISO North and the Central region, North Central and the MISO South region. So that definitely imposed challenge to manage the North and the South flow there. So another mainstream flow pattern. So in addition to these two major flow patterns, we also have those local areas, what we call load pockets. Those areas are usually have limited importing capability. So the loss of generation and the transmission lines in this area definitely caused the emergency situation in this area. Actually, just illustratively, in the north, we have the central Illinois, we had a local emergency, and also in the south, we have the western load pocket, and then Louisiana area. So those areas we actually had the local transmission emergency because of the stress on the transmission lines. So hope I was able to replay the stressful situation after several months. Now, especially we are getting ready for the hot weather, but I still vividly remember the stressful situation with people across operations working almost 10 days straight to prepare for this event. So the preparation ahead of time definitely played an important role to manage the extreme conditions. Actually, the preparation starts from months or even years ahead. Just a few examples. Every year, MISO hold this winter readiness workshop with our members to outlook our supply and demand condition, including those generator winterization and the fuel survey to get a visibility on the resource availability. And also periodically, we perform operation drills with our members, especially to prepare those extreme conditions where we will call on the emergency only resources, because we don't call on these resources all the time. So we do rely on this drill to get everybody ready whenever the extreme event might happen. And since 2016, MISO start to see more of these extreme events. So after every extreme event, MISO will work with our members to review, do a post-event review, to look at the lessons learned, and also to seek any opportunity we can improve to better prepare for the future. So one of the examples is really after 2019, the January emergency event, we actually look at the over forecast wind and then made an improvement to include the cold weather cutoff as a parameter in our wind forecasting model. So that definitely helped a lot to better forecast wind during those cold situations. So now comes to weeks and days or even hours ahead. Weeks ahead, we start to closely monitor the developing weather pattern. We actually have a meteorologist update to our operations every day, and then evaluate the involvement risk as the forecast improves, getting closer to the operating days. And based on those information, we coordinate with our members, do the outage coordination and gas electric coordination, get an idea of where the generators, the availability stands. And also, we effectively communicated the anticipated situation with our members through multiple communications, such as the cold weather alert, capacity advisory, etc. And during those communications, we work with our members to put a request to update their availability and they true up their offers. So all those helped to give us more better situation awareness. And directly after the extreme events, we and our members took collaborative operation actions to maintain the reliability. On the commitment side, we have a multiple stage commitment process from multi-days ahead to day ahead and then to intraday or hours ahead. So we actually made commitment ahead of time based on our assessed risks. That actually really helped our members to procure fuel. And also we extended the start stops, realizing the risk that some generators might fail to start during the extreme cold. So we actually extend the start to mitigate those risks. And that helped us to maintain a lot of the visibility of this unit during the high demand times. And during this event, especially the 15th, 16th, and 17th, we actually went into very emergent situations, including the whole South region, a capacity emergency, and then in some of the local areas, we talk about the local transmission emergency or transmission system emergency. So that really demonstrates the value we have been preparing over the past to have the well-established emergency operating procedures and the periodical drill that allow us to really get the situation under control over the stressful situation. So those emergency operating procedures really developed for those situations that might have a negative impact or actually have a negative impact on the system reliability. So definitely we see those play an important role during the event. So now, like looking forward, this event actually gave us valuable experiences and highlight the work we are doing under our responses to MISO's reliability imperative to not only address the current challenge, but also look at the future. We definitely see the further grid operation challenges with the changing landscape, with the resource portfolio rapidly shifting. It will become more prone to weather. So that really will give us a potentially different risk profile from those weather-dependent resources, and also like the more likely, more frequent extreme weathers. So all these really emphasize the needs of adequate, rampable, and deliverable supply. So adequate, a lot of us know, like it's really to maintain enough supply to meet the obligation. Rampable here, we start to realize we not only need to have enough supply, but also need to have flexible supply so that they can be moved up, ramp up and down to manage when system condition changes fast. And I do want to emphasize the deliverable capability here, because that's directly translating to the transmission capability. So it's extremely important for us to be able to transmit the generation to where it is most needed. So look at these challenges. We really have the work organized in 4 areas, including market redefinition, long-range transmission planning, operation of the future, and the market system enhancement. So particularly for this event, it definitely highlighted the importance of the sub-annual resource adequacy construct, and also the better accreditation of resources to help with the fuel assurance or winterization. And particularly for the operation side, we see the importance to better project the system conditions, effectively capture the weather risks, and better assess the uncertainties on both supply and demand and transmission system. And finally, effectively integrate all these unknowns in the operation decision-making and the planning process. So with that, yep, I think that's the end of the presentation. I really look forward to the discussion at the end.
Congcong, that was great. Thank you so much for sharing the perspective and explaining how MISO weathered the event and the importance of the collaboration with your neighbors. So really enjoyed hearing that experience from you. Josh, right on cue. Josh is no stranger to ESIG events, so glad to have him here to talk about some of the extreme weather analysis. Folks, last reminder, please get onto Slido, add your questions. We see more coming in. As soon as Josh finishes his conversation, we will go ahead and start having a review of those questions and open up the line for all the panelists. Take it away, Josh.
Great. Thanks, Aaron. And thanks to the earlier presenters. It's been a great panel so far. So hopefully I can finish it out strong here. So we've been talking so far about kind of the cold weather events and how that might be associated with climate change, and then also dove in a little bit more specifically to the winter cold wave in February 2011 or February 2021, and what that looked like from a system operations perspective and a meteorological perspective. What I'd like to wrap up today with is looking at these types of cold waves, not specifically the cold wave we saw back in February, but cold waves generally, and what they might look like from a system operations perspective when we have a future power system getting a lot more contribution from variable generation sources, specifically wind and solar, and trying to understand what some of the challenges and opportunities there might be when we look at these types of events in the future system. So this generally is coming from a project that I've collaborated on with Justin Sharp, who we heard from earlier, looking at weather events within the NREL resource data set, and then applying those to our production cost model to understand how the system operates through these events. I just want to highlight that this is still unpublished. We're within a few weeks of actually publishing our actual technical report, And so we've received some initial review. We've been using eSig as a opportunity to review our findings and our methods throughout, including multiple times at this particular eSig session, the meteorology, the forecasting and markets workshop. So this is a nice opportunity to kind of wrap up and give everyone a sense of what we've been working on, especially as it relates to cold waves. So just to remind everyone of what we've done with this project, the idea here was to identify weather events within our resource data sets and break them up into two categories. First, look at newsworthy weather events, so things that historically we would have seen show up on our local news to warn us about that these were coming and may have actually had large power system impact when they did occur in the past. And then also identify a set of events that wouldn't actually make the news. The weather itself is relatively mild, but it does have a large impact on the wind and solar generation potential due to its widespread impact. And then try to understand how those different events play out in future systems. So on the right-hand side, we designed 3 different future power system infrastructures that have increasing penetrations of wind and solar, and these will be the basis of our analysis that we look at later. So the 3 correspond to 3 different years into the future. We have a contemporary system, which is around a 17% wind and solar penetration on an annual energy basis. Another one that's 50%, and then the final one that reaches 65% wind and solar generation on an annual basis. You can also see the maps to generally kind of see where wind and solar goes. You can see it goes all over the place by the time we reach the 2050 system. These are the basic resource data sets that we use that we have available to us at NREL. The Wind Toolkit, the National Solar Radiation Database for solar resource, and then also mining EIA data for hydropower resource to correlate all 3 of those renewable resources together so that they're subjected to the same meteorology when we're doing this modeling. And then we also have a robust transmission infrastructure database with load resource information that also is time synchronous with these resource data sets. The key that I wanted to highlight here is that we were only looking at weather that occurred between 2007 and 2013, and right now that's because we're limited by the Wind Toolkit. There are efforts to expand that so that we could get beyond just these 7 years. That's what we looked at for this study. Another improvement we made to system operations modeling for weather events was to better capture weather-correlated thermal outages. This is based on work from my colleague Sinnett Murphy during his PhD that correlated temperature to the probability of outage for various resources. So, for example, we know all of the impacts to the thermal fleet that occurred during the February winter event in Texas and throughout the system. And so we're trying to capture some of those. It is only a first order understanding of this correlation, though. So once we do publish this, we have a variety of events, not just cold waves, but we've got heat waves, we have some hurricanes, and then we also have all of these various events that we identified that have a widespread impact to the wind and solar resource throughout the country. In the report, there's a weather narrative that was authored by Justin Sharp to help us to merge the meteorology and the system operations into a cohesive narrative to understand how these might play out in the future system. Okay, so with all of that background, I want to dive in a little bit to our specific cold wave finding from the study to kind of wrap up the discussion from today's panel. So generally, what we found is that that operations evolve during cold waves, and a lot of this evolution is driven by what's going on with the wind resource. That's not to say that the solar resource doesn't also have an influence, but it's a little bit harder to tease out, and it changes a little bit more from cold wave to cold wave. While there was a pretty clear trend of what was going on with the wind resource in our case studies of cold waves that we looked at. So the GIF that we're looking at here is of the February 2011 cold wave. Sorry about that. February 2011 cold wave that there was all sorts of discussion about during the cold wave that occurred just this past year. Given that there was a large FERC and NERC report that discussed this. But what we see during these cold waves is that as the cold comes through, which is the image on the left-hand side, as the cold comes down, we see a really strong wind resource being associated with that initial front. And then on the right-hand side, we see the actual wind generation potential during that same time. So looking as the front came through, we saw a strong wind resource throughout. Let me just restart that. So on the 1st of February, we see the strong wind potential coming through the SPP territory down into Texas and throughout northern MISO as that cold starts to move across the Eastern Interconnection and Texas in the US. But as this cold wave, as the actual front itself moves on, what happens with the wind resource is a little bit uncertain from cold wave to cold wave. So in this particular event, we actually saw quite strong wind in the northern areas of MISO, as we're seeing right now, during after the cold wave has left, but the cold itself persists. Whereas there's other places like the southeastern United States and parts of Texas where the wind resource is actually quite poor during this time. But that doesn't mean that that's the way that this occurs through for all cold waves. So what we're looking at here is a comparison between that extreme cold wave that occurred in February 2011 and a more mild version of the cold wave that occurred in February 2008. So these maps here, any area that is in blue shows above average wind resource potential, whereas the red areas are below average wind resource potential for that particular day. So if we look at the more mild version of the cold wave, we see widespread below average wind potential. It's not to say that there's no wind anywhere, but it's well below average in some places, and it's pretty widespread for these 4 days that occur after the actual front itself has moved through. And that's kind of a general finding that we found from looking at a few different cold waves, is these more mild versions of the cold tend to lead to this stronger lull, both spatially and temporally, of the wind resource. But generally, there still is this lull that occurs in the more extreme cold waves. It just isn't quite as strong, and there are some pockets where there actually still continues to be strong wind resource. So now we're going to apply. We're going to look at the system operations results from our production cost modeling of these events for 2011 and the 2008 more mild cold wave, for the 3 different infrastructures that we discussed before. So these are dispatch stacks looking at the hourly generation for every generation type. So we start with nuclear on the bottom, followed by coal in black, gas combined cycle in purple, and then the blue areas is the wind generation potential, followed by the gold PV generation at the time. So if we look at the initial front coming through on these dispatch stacks, we see really high wind generation potential, just as we saw on the last few plots. As that front moves through, really strong wind. By the time we hit the 2050 infrastructure system, wind and solar generation are providing about 80% of all generation potential in the Eastern Interconnection. I should have clarified that these dispatch stacks are only the Eastern Interconnection that we're looking at here. But this period that follows as the front moves on, but the cold persists, is really where there's uncertainty and where we need to better understand these events so that we can ensure that we have enough resources to operate through them. So if we look at the 2011 extreme cold wave, there was a decrease in the wind, but during this time where the front has moved on, but the cold persists, we're still seeing about 50% of all generation coming from wind and solar, even as that load remains elevated. In contrast, the 2008 more mild cold wave, we hit periods where overnight, when solar is no longer generating, where we hit wind penetrations below 10% of all load, and that's being filled in with our available thermal fleet, which in this case, by the time we get to 2050 and even 2036, is largely gas dominated. And you can see the lighter purple areas are combustion turbines, which tend not to operate for extended periods of time. But in this mild cold wave version, we see, I'm just going to try to grab my laser pointer here. In this mild cold wave version, we see these gas turbines on for an extended period, and this just demonstrates the lack of wind resource that we see during this time. We do also see an impact to the thermal fleet. As I mentioned, we have the correlated outages of the thermal fleet based on temperature. So in MISO and SPP, we're seeing elevated outages of the gas fleet and then requiring most available gas to be turned on during this time to maintain adequacy during the 2008 more mild cold wave event. So let's take a look at transmission during these two events, because as we saw in the GIF earlier, during the 2011 cold wave, the more extreme cold wave, we saw good wind resource, but in pockets. The southeast of the United States and even down into Texas kind of had somewhat mediocre wind resource, while as northern MISO had quite strong wind. So really, we're going to rely on our transmission infrastructure, which is expanded in our 2050 system and 2036 system, to be able to share that geographic diverse resource to operate through this cold wave. So it's really transmission that's enabling this. And if we look in the 2050 system, this orange time series is the net interchange between MISO and its neighbor PJM to the east, where there was a decrease in the wind resource. We see a swing from 7 gigawatts of MISO importing from PJM as the cold wave was actually moving through. And then as the cold wave has moved on, we see over a 24-hour period, MISO changed to be a net exporter of more than 15 gigawatts of power to PJM. This is really it sharing its wind resource with its neighbor in PJM, and then further PJM sharing that power with Circuit and ISO, which were even more further impacted by the lack of wind generation potential during this period. Even in the 2008 milder cold wave, transmission is also enabling the sharing of geographic diverse thermal resources. So on the last slide, I mentioned how SPP and MISO were both getting pretty tight on its available thermal resources to be able to dispatch in the event that load would continue to increase or wind or solar would decrease even further. But the cold wasn't quite as strong in the Atlantic states in PJM and CERC and NISO. So in this case, during this period, we see PJM, which again is in the orange, exporting along with some of the other neighbors in MISO, exporting to MISO, who in turn is exporting to SPP. So much very similar to what Congcong was mentioning that occurred between PJM, MISO, and SPP during the February 2021 cold wave event. So we're relying on this transmission infrastructure to help us through this event in these higher penetration systems. A couple of other points that I didn't really touch on in the comparison of those two cold waves is icing of turbine blades that would shut down wind generation, or cold temperature shutdown limits that Congcong mentioned that were widespread during the 2019 cold wave that occurred in MISO. So in our investigation of wind icing, we never saw anything CONUS-wide, so across the Western Interconnection, Eastern Interconnection in Texas, that led to wind D-rates greater than 10%. So this is a D-rate of total wind generation potential, but relatively small if we look at a wide enough geographic area. However, local impacts can be quite strong. So the plot on the top here, we're looking at a blade icing event that occurred in February. This one is in February 2012, where this red area is the D-rated wind generation due to icing or cold temperature shutdown. And we can see periods where we're well over 50%, upwards of 75% of all potential wind generation reduced due to icing and cold temperature cutouts. And really, to make up the gap here, we're seeing a change in the net interchange between MISO and, or I guess Minnesota and Wisconsin in this case, and its neighbor in the base case situation where we avoid icing and low temperature cutouts. There was more exports going to the Chicago area. We now have to cut those off in addition to turning on local gas generation. And as we've already mentioned, we know from experience from multiple cold waves over the past couple of years, the gas infrastructure is particularly sensitive to cold waves. So this is just an example of the MISO gas generation fleet during another cold event, the December 2013 set of winter storms that moved through the country. We see elevated amounts of gas going out during this time. So it is certainly kind of a compounding of events if we're to where you might have a derated wind generation due to blade icing and local gas going out at the same time. So better understanding the correlation of those risks will be important to understand, even though the impact to the overall wind generation fleet throughout the country, there isn't a ton of risk for widespread derate due to icing. So with that, I'm going to wrap up and just kind of summarize some of the points that I think are most salient from what we found in investigating cold waves for higher penetration systems. So as I mentioned a few times, for cold waves, that spatial and temporal extent of the wind lull that follows that initial front, that initial cold front, is uncertain. And while we didn't really get into it in this study, it's pretty clear from looking at some of the historical cold waves and the operational forecasts that are used for wind generation capture this pretty well. There's an understanding that there's going to be this lull in the wind that follows the initial front. But the real question is, how well do resource adequacy studies understand this? And that's going to be what's really key for making sure that we have the appropriate amount of resources, whether that's generation, storage, or transmission, to be able to operate adequately through these events. With our limited sample size, it really looks like these mild cold waves are more concerning in terms of the lull that occurs after the initial front. But I do want to emphasize this is a limited sample size. We only grabbed case studies from a 7-year period from 2007 through 2013. Across all of these, we saw that transmission was operated quite differently than the contemporary system. So the 2024 system was relatively consistent magnitude of transfer of power between regions. In the 2036 and 2050 system, we saw more dynamic operation, not only greater magnitudes, in part enabled by greater transmission expansion, but also a changing of direction of flow from day to day as the wind and solar resource changed during the event. And finally, just a few points on next steps. So we're hoping to increase our wind, solar, hydro, and load data sets to capture more types of weather events, and then also capture the longer atmospheric trends that occur. So certainly understand that weather can change not just seasonally, but also over a longer period of time, on decadal timescales at times. And then in addition, making sure that we're having a sense of how climate change might change the frequency and magnitude of some of these events. Finally, we'd also like to improve the operational and resource adequacy modeling of weather events. We stepped through how we modeled some of these events. Our next step is to better quantify some of the impacts of these events to provide metrics for planning, so that when we go back to this question of, well, we can operationally forecast these events well, but how do we tell resource adequacy studies the risks that these events pose to the future system? So with that, I'll leave you with an image of Hurricane Gustav here, and thank you all for your time, and I'm really looking forward to the discussion. So Aaron, back to you.
Hey, that was great. Thanks so much, Josh. We'll let this video play out, and then I'll have you stop sharing your screen so that we can have all the other panelists turn on their camera and we can start going through the Slido questions. There we go, Julie. Great, thanks. Just waiting on Justin and Congcong. There's Congcong. Awesome. Thank you for turning it on. If you don't have the Slido questions in front of you, it would be great if you can turn them on. I promise I did not submit those transmission questions. Okay, folks, I'm just going to throw that out there. I am not only kind of a fanboy, but we've got a couple good ones. So I'm going to tee them up and we're going to just kind of go through them in ranked order. And then I'll probably choose a couple from the bottom that maybe haven't had us enough time to get upvoted to the top. So this one will go broadly. There's a couple questions that are targeted for individuals. So we'll go through those in order as well. But the first one is we saw how helpful energy from MISO and PJM was to managing the central United States extreme weather event. What would have happened if we had transmission to the west? Was there any benefit or excess generation or positive weather conditions that would have made it even easier to ride through the storm? Anybody?
I'll get started. Oh,
go ahead,
Justin. So I'll just quickly start. So I see this is interesting scenario, definitely. without an actual simulation study, because transmission system are quite complicated. I'm more humbled the more I'm getting on the operation side, so I cannot speak like with more confidence without that study. Just conceptually, like I think the better the transmission system is, the better it can help to get the supply to where it is most needed. I do know, like with all the solar in the west, and also like wind we have in our north region, and then the gas resources. So it will be like good to have those capability to transfer whenever the supply is accessing certain region to the other side where it is most needed or constrained or in short, yeah.
Awesome answer, and I think appropriately reserved, right? Because it's really easy to play a bunch of what if scenarios. There's all sorts of what ifs that would have made the event more manageable, but a little bit of prudence here is needed so that we don't make rash, very expensive or inappropriate responses to this real event that should be managed in an appropriate manner. So I really appreciate that one. Josh or Justin, I couldn't tell if you guys are trying to chime in as well.
I'll just chime in real quick, and I'll keep it really short. I'll just get on my soapbox real quick. If we're going to do high penetration renewables at 80-90%, it is absolutely crucial that we build out a transmission backbone so that we can look at the system holistically Basically, we have to have a transmission system that is on the scale of planetary waves. Otherwise, we're going to really struggle to do it, and that's the bottom line. And we need to get real about this. And I'll leave it at that.
Awesome comment. Julie, Josh, do you guys have anything to add? Otherwise, I'll go to this. I think we covered the top two questions. Go ahead, Josh.
Maybe just really quick. I mean, I think that the example of PJM going to MISO to SPP is just a great example of the value of transmission to provide resource adequacy. We've already hit on that a few times. Colorado, New Mexico were severely strained by this event. Also, there was very tight gas margins, certainly using on-site oil instead of the gas infrastructure. So there's no doubt that the closest neighbors to ERCOT in the West would have also been tight on supply, but just like we saw in the Eastern Interconnection example, many times it's your neighbor's neighbor that can help you out there. I don't actually have anything useful to say about what was happening in CAISO at the time, but certainly something that's worth thinking about when you're thinking of these studies. But also just generally resource adequacy planning, kind of really understanding this broader scope that weather impacts the entire nation in different ways. It's important to kind of capture that impact when we're doing this type of modeling and looking beyond just our individual region.
Awesome questions. And I'm going to just take one moment to do a little ESIG promotion here. We've got a resource adequacy task force, which is part of the system planning working group that is looking at some or many of these different topics. And it just so happened that we'd started up that task force ahead of these extreme events, whether it was the California heat wave or the Western heat wave, or the ones that we saw in the central United States. So if you're interested in learning more, you can reach out to me or to Derek Stenslick. We're leading that task force, and you can find out more. The coolest thing I think we've been doing is trying to characterize these events based on size, frequency, and duration so that you can recommend the right mitigations for the types of events that we expect to have happen. Julie, I've got a question teed up for you right here. What do climate modeling studies and data say about the likelihood of colder winter temperature events in the Midwest regarding the magnitude, frequency, and duration?
Thanks, Aaron. That's a challenging question, and I did a quick little survey while we were looking at these questions, and I was able to find 4 studies quickly, and 2 of which said that they were going to be more likely, and 2 of which said that they were going to be less likely. So I think that this, unscientific sample underscores the tremendous amount of uncertainty that comes into trying to understand not just which scenarios are you going to use in forcing the climate models, but then what is it going to happen? Which parts of the physics are included? Are they included appropriately, and so on? What I think is kind of interesting is that one of these papers said, we know we don't have the answers right now, but we also know that policymakers need some sort of answer. So there's an impetus, or there's movement going towards uncertainty quantification to give better answers. But I can say that right now, I would not necessarily trust any one individual study if it says that these are going to be more likely or less likely going forward. Sorry to not have more like clarity, but my crystal ball is in the shop right now.
I think that reservation in terms of jumping to conclusions is appropriate and keeps our science and analysis valid. And so I think that's a responsible check. I'm going to go to the next question unless I have another response from somebody. This one's from Mark O'Malley. So capturing these extreme events and planning is really expensive, folks. There's a reason why we only plan for plausible events and not all events out there. I think that's a great point. He assumes that MISO and other system operators simply plan to be able to operate through them as best they can to some threshold and then focus on recovery. What do folks think about that? Congcong, do you have any comments on these planning thresholds?
Yep, I do think that's a great question. Like for us, we always balance between do you want to cover 100% or 99% of the confidence interval or 95%, because it is costly to go like further up to like almost to 100% of the confidence interval. So that's why like for the planning side, I do know like the sub-annual resource adequacy construct is trying the best to align with what we see in operations. And then for operation side, when we develop all those flexibility requirements, we try to balance between the cost and reliability, but do try to capture the extreme events. Not those kind of example could be a dynamic requirement, right? So like when you forecast the normal condition, you might carry a relatively modest amount of reserve, but when you have those leading indicators of extreme events like this weather pattern, if you can identify early enough, you can start to prepare for more extreme scenarios. And then also emphasize the need to have forecast the leading indicators of those extreme events, definitely like collaborative with the meteorology world and other industry. So that's definitely a very good opportunity there too.
Go ahead, Josh, and then we'll go to you, Justin.
Great, and I think Mark, your question is a good one. It's something that we have to be careful about. I think one thing that Justin and my work really wanted to try to emphasize is we need to understand what are the events to be concerned about and what are the 99th percentile of events now and what do those look like, because we think those are changing. Not just because of the weather itself, but the resource mix and making sure that we capture that in our planning and not just kind of plan to peak loads anymore.
Thanks for giving me the seg that I needed there, Josh. I wanted to just quickly jump back to the climate change question because I feel very passionately about this. The question is a good question. It's a fair question. But at the end of the day, whether or not we're going to have slightly more cold waves or they're slightly colder or slightly less, Julie, as Julie pointed out, we don't know the answer to that. The science is really, is in process right now. But more importantly, we have much bigger problems. We are trying to move to a system that is going to be high penetration in renewables. The impact of climate change on that added weather variability is trivially small compared with the impact of the variability that we're putting onto the system. And I wanted to make that point really clear because it's coming up again and again and again.
I think that's a great comment, Justin. One other comment that I saw buried down deep in there is what was the cost estimate for all these outages and the societal impact of it? And then the comment was, how many peaker plants or transmission lines do you think you could have purchased with all of that lost economic opportunity? I don't know if anybody's seen those numbers on the panel, but it might, kind of round out the question that was being asked by Mark. Anybody? Oh, I just see grins and smiles. So we're going to move ahead on that one because I think we know it's got at least 7 zeros probably. This one comes from Australia, and one of the things that just makes me so happy to be present on these calls is all the diversity and perspectives that we get from the panelists and from our participants. So we've got one from Australia. I saw individuals from across North America, Europe, South America. This is great to have this much perspective at this time of day on a Friday. So thank you, everybody that came in. Josh, this one goes to you. So your 2050 scenarios have an awful lot of fossil fuels.
Yep.
Come on, where are we going with this?
Yeah, I think there's probably a great joke somewhere about changing priorities of different administrations, but I'm not even going to try. So I think this is a super important question. There is some ongoing work at NREL that is looking more and more about, okay, let's if decarbonization happens quicker than what the scenarios that we used for our study was, then how does the system actually evolve? And we're applying the events that we identified here and seeing if those change. So far, without getting too much into some of this other work that's ongoing, a number of these events had such widespread impact to the wind and solar resource that they are still the most relevant in our 2007 through 2013 weather data set. But I do want to emphasize, I think the more important piece will be getting a larger set of weather to consider, given that we had such a small sample size. So I think this is a good first step, and we need to both understand more weather events and understand a quicker transition to a decarbonized system than what we modeled here. Though I do think that this will be important for understanding the transition to that decarbonized system.
Awesome. Hey, Julie, thank you so much for dropping that link in the chat to the paper that quantified the financial impact of the recent event in Texas, $130 billion. Josh, do you have any idea of how much transmission you could build for roughly $100 billion?
Yeah, there's some studies out there that get kind of right at that number, aren't there? Yeah, no, there have been certainly segments of kind of proposed macro grids out there, and certainly not just things in the SEAM study is what Aaron is referencing. But definitely, it's a lot of money that could be spent for infrastructure that may have provided some benefit through that. And there's been a few. Well, I don't want to go too much into other studies, but that's definitely one of the questions we're looking at. Is how could would this have paid for some of this infrastructure, and how much does it help?
Or even if ERCOT had just had a relatively small link to somebody else.
Yeah, so awesome. Let's move ahead, folks. We've got a really great question here that I think touches on the point that got you so watching your data feeds, Justin, was what was that mechanism for that sudden stratospheric warming that disrupted the tropospheric flow? I had never heard of that SSW before. So how do we know when that happens? It sounds like I want to watch out for it.
Yeah, so that's a great question, and I saw it came from Bob. I'm going to punt it somewhat because I am now at a point in my career where I know what I don't know, and I understand the basics of the cause and effect, but I don't understand the dynamics. I'm not sure if Julie does.
So I'm not sure if Bob's question was, why does a sudden stratospheric warming happen, or once it happens, why does it mess up the troposphere? So the second part is a little bit easier to answer. But Aaron, if you're wanting to look out for SSWs, there's a lot of public weather agencies globally that keep track of them, and all winter they'll be sending out alerts about those. Anyway, the way that they disrupt tropospheric flow is that they basically leverage off those wavy patterns that I had showed. Some of those waves tend to be longer because of the way that North America and Northern Asia, the land-sea contrast happens. So once you have a sudden stratospheric warming, that plus these very long Rossby waves mean that instead of everything continuing to rotate in an eastward direction, then we get these slowing and kind of blocking events. So once that happens, that sets up the cascade for the disruption of the tropospheric temperatures and the mid-latitudes and the winds and so on. So Bob, I'm not sure if that answers your question. You can ask another one if you wanted to go in a different direction, but that's the kind of the quick 2-minute.
No, I think that's a great sorry, I was reading the comments coming in from O'Malley at the same time, trying to do too many things at once. No, Julie, I think that is a great answer, and I think you guys all know Bob, so if he wants to drill in more, you can probably talk with him. But I think it gives a nice perspective to the others on the audience that were like me and hadn't heard of one of these type of events and what to look for. Okay, here's another one from Jennifer Newman. For Justin, was the 1983 cold event associated with a similar synoptic setup as the February 2021 event?
I do know the answer to this question. I almost, if I saw my deck was already too big, I had actually downloaded all the data from 1983 to check it against it, and it is very, very similar. I mean, it's not a carbon copy. There's obviously a lot of different nuance. But yes, it had a West Coast blocking ridge. The Greenland ridge was in place, and basically a strong trough through the middle of the country, and it looked very similar. If anything, it was more blocked.
Interesting. I'll have to talk the next time we get together in person, Justin, about those blockers and how pervasive they could be, because I have a whole bunch of questions about that.
You know, I know Jennifer well. She's interested. Just tell her to drop me an email, and I'll be happy to give her the analyses that I downloaded.
Yeah, I think, you know, she had the follow-on question about how unprecedented that event was on a regional basis, not just the Texas basis. So you showed how extreme it was for Texas, but
it was
the
extreme.
geographic scope.
Yeah, including like Oklahoma and all the southern states. It was a big event.
It was pretty darn cold up here in Minnesota, even by our standards. So, definitely had a large geographic.
Oh, you mean the February event? Yes, it was.
Yes.
It had a pretty big scope as well. Yeah, that's right. And so did 1983.
So I feel like we've touched on. I've got this question here that's about the interconnections and transmission. I feel like we've hit that one. Let's go to the other one that's about electricity prices. Josh, when you look at all those models and you do your simulations, what kind of LMPs are you seeing out with those extreme cases?
Yeah, I mean, I think I can mostly talk about the differences between essentially the two cold waves that we're looking at. And we're seeing very high prices. I mean, we're not modeling any dropping of load in these two cases. So the model actually had adequate generation to provide the reserves and serve load during these times, but we're getting tight. And you know, I think as indicated by in that mild cold wave where we've got those gas combustion turbines on for such a long period, it is demonstrating how kind of tight we are. You know, those aren't resources that we like to use for that long of a period, especially the ones that we were modeling. But yeah, you know, much more expensive to operate through the mild cold wave. I don't have the actual prices in front of me, so I can't really say. But we're talking about, you know, $100 plus per megawatt hour prices in our model, which is kind of pretty high for our model, and then, you know, relatively low prices since we're at 50% wind and solar penetration in the 2011 more extreme cold wave. As that cold persists, just a much greater contribution from the variable renewable resource.
Yeah, and I think the other thing we've talked about in the past at these types of events is the difficulty in forecasting LMPs out in these futures with power system transformation. And so there's a bunch of things we don't capture in those models, whether it's the scarcity pricing rules, the correlated nature of the natural gas pipeline and the electricity system, and how the interactions between those might drive prices. So lots of uncertainty there, and a pretty tough thing to gather. Let's see, we've got another one here. I think this one's going to be for either Justin or Julie. Can you talk about the challenge improving a counter trend from the Arctic amplification enhancing cold extremes within the strong downward trend in cold extremes? I think I understand that one. Do you guys get it?
Yeah,
so take that one first, Julie.
I'm sorry, Justin, you want it or you want me to do it?
No, you go ahead if you want.
Okay, so thanks, Keith. That's an interesting question. You know, it's always a little bit of a challenge to prove, you know, correlation and causation and things like that. And so I think you're asking about how can you say that we're looking at trends in cold extremes, meaning the coldest weather, how is that changing year by year when we're looking at overall, daily average temperatures increasing? I think that that's what you were asking about. And I think that that just makes it a harder question, but I know that when you have hourly resolution temperature data, it is possible to do that. It's just tricky to find statistical significance when you have numbers, very small numbers of rare events. So, this is a challenge and people are working on it. But as I've said repeatedly, I don't think that there are any clear answers about necessarily the causation of these types of events being related to climate change right now, or what will happen in the future. So we just have to be careful. Justin, do you want to add to that?
Yeah, I can add to that. I actually had some really interesting conversations. I talked with Jennifer Francis, who came up with some of the original wavy jet theory, and also with the Texas state climatologist John Nielsen Gammon, and a couple of other folks, and got very differing views on it. That really is representative of how much uncertainty there is within the academic sector right now with respect to this stuff. But it does appear that, to me at least, that, and I'm going to speculate a little here, that ultimately thermodynamics will win. If you've got warmer source air, you simply can't get as cold of a cold wave. I mean, you can have them become more frequent. You could have them reach further south, but ultimately the source air is warmer, and that was John's sort of thought on it. But again, to sort of come back to what I said before, the relative impact of these compared with the impact that natural variability is going to have on a system that is 90% renewables is small. We're looking at changes in something. It's the second derivative essentially of the change that's occurring, versus the first derivative is the fact that we're making a system that is completely weather dependent. I'm going to harp on this because it's really important that people start thinking about it. There's just been a 2-day conference that's focused entirely on climate change, and I'm kind of ticked that we're focusing on the wrong problems, in my opinion.
That I think the point is well taken, and glad that's why we invite people back to help amplify the message. I think the other one that comes up is, yes, it's important to look for these cold waves, but also watching for the heat is probably something that becomes particularly important, as we're seeing for the operators today. And I know my air conditioning is already turned on up here in Minnesota. And 95 degrees and muggy is uncomfortable. Feels like Florida. So, okay, we had another question that is slightly lower down, and then I'm going to come back up to Will's comment. And I think this goes back to what you were saying earlier, Julie, a little bit of confusion about causation versus correlation or consensus on whether or not the Arctic amplification problems that we were seeing are resulting in these extreme events, if I got that correct. So, what do you think there? Like, can we say it's correlated, but we can't prove causation, and we don't have consensus?
So I think that the bigger issue is that there's not consensus, and I think that I'm going to combine this with the other question that was asking about why the observations and the models had a different story to tell, because I think that those are related. When you're trying to build consensus, you need to be able to analyze a data set in many different ways and come to the same conclusion. And I think that the fact that when you analyze observational data sets, which are really reanalysis data sets, which have a lot of model data in them, you can slice and dice the data in many, many different ways. And so you can accidentally sometimes imply that there's a relationship when it isn't actually there. And so the fact that there is a different perspective when you look at observations as compared to when you look at model forecasts, I think points to the difficulty of finding consensus. And I think that we're trying to analyze a very complex system, and we have great tools, but they're not adequate to the task yet in order to give us a very clear answer about what is causing these types of events. But I want to underscore the point that Justin is making, which is this is an interesting question, and questions where more research is required are always interesting, but it may not be the right question to be asking right now when we have other pressing social demands. And so it's fun to think about, but the people who do this day in, day out do not have consensus now. So maybe we should stop seeking that and focus instead on how do we get the transmission built.
Awesome comments. This is great. So I've got another question here from Will Holmgren. What could have been done differently if 1 to 7 day ahead forecasts had been more accurate? Or were the resource constraints so extreme that forecast accuracy was functionally irrelevant?
I can add some thoughts here. I would say forecasting accuracy is always helpful because like at least for the load forecast side, you can have less risk. You need to worry about it. Of course, during this particular event, we face risks from every dimension. So like given the supply side risk, we might still make the commitment we had done. But just in overall the planning process, when every component, if we can have better certainty or better accuracy there, that can definitely help with the risk management ahead of time. Yeah.
Oh, folks, I just realized what time it is. I'm supposed to be handing this back over to Charlie at the end of the hour so he can close us up. So many great questions to the people that stayed on to the very end. Thank you so much. Please follow up directly. You can either reach out to myself or Ryan, and we can connect you with the speakers if you can't find their email addresses. But Charlie, why don't you wrap it up for us?
Okay, thank you, Aaron. I would really like to join you in thanking our panelists and thanking you for the great contributions and discussion today, and thank all of those that are on for your participation. To me, this has been a really fascinating discussion on the changing impact of climate, meteorology, and resource mix on system adequacy. And just as a reminder, we will follow up with written answers to the questions we didn't get to during the Q&A. I would also like to remind you that the Meteorology and Markets Workshop sessions are being held on Tuesdays and Thursdays throughout the remainder of June. We have a session next Tuesday on the state-of-the-art of probabilistic forecasting and its use in operations, co-chaired by Ben Hobbs of Johns Hopkins and Aidan Toohey of EPRI. There's no charge for the sessions, and you're all invited to attend. Further information on registration is provided on the ESIG website at esig.energy. Thanks again to our panelists and participants. Stay safe, and we look forward to seeing you again on Tuesday.